Hello everyone, welcome back. Today we will start a new lecture series in which we will learn how to use analog to digital converter in FPGA. So analog to digital converter is used for closed loop system. So we will do how to use analog to digital converter in FPGA to make a closed loop to control the output or anything you want. Okay, so let's do start. So first of all, what we will learn in this video. So first we will see why ADC is required. Okay, and the second is for ADC we need one IP block which is XADC Wizard. I will tell you why XADC is required and what is XADC. Okay, and the third one, we will do simulation in MATLAB using Xilinx block set. Okay, and we will verify our simulation model. So our ADC is working or not, we will do simulation and verify it. After verifying, we will do the same thing in hardware. Okay, so stay with me. So let's start. So first of all, why we required ADC? So ADC is analog to digital conversion. So if you are using microcontroller for controlling, then you required ADC. So for conversion, since our system is analog but microcontroller takes data in digital. So what we do, first of all we need to convert analog to digital, then inside the microcontroller we will do controlling things. Okay, here you can see the sensed voltage in simulation. The output voltage is V0. Now what we do here, I have a comparator suppose. Okay, so input voltage is coming, which that is sensed from the output, and this is a reference. Suppose I take it Vref. This is the reference. Maybe it's depend on how much you want to regulate this. Okay, so regulate output voltage. What we do, we have to do a control. We have to make a control loop. Okay, so this is, suppose this is a control, then this is plus and minus. Okay, and now after this, comparing with the error signal is fed to the PI controller. Okay, PI controller, this is our controller, and this controller generate one control signal. Okay, control signal, PI controller generate control signal. This control signal is compared with what we have done already in our previous videos, where this control signal is compared with a sawtooth. It may be sawtooth or triangular pulse. Okay, we compare, this control signal is compared with sawtooth signal. Now this in output, what we get? In output we get pulses. This pulse is fed to the switch gate. Okay, I hope you all understand. Suppose we want to control output voltage of 100 volt. Okay, so control loop operates such that the output voltage according to controller it will decide gain, and this gain according to the control signal it will generate a pulses. Okay, by comparing with a sawtooth signal. Okay, so this block, these things, this whole things, choose black. If you see this whole thing, like comparator to PI controller to reference, these whole things are inside microcontroller. Okay, so that's why we need here, suppose this is our analog signal, voltage output is analog. So what we do here, we need a block to convert analog to digital. Okay, so here we need analog to digital converter to convert analog to digital. Okay, and these whole things, that is comparator, signal, sawtooth, PI, whole things are inside the microcontroller in digital form. Okay, that's why I hope you understand why we need ADC. Okay, now move to the next. So as I have told you in second, we need a XADC Wizard. So first of all, what is XADC Wizard? It is a IP block. It is a IP block in Vivado. Okay, this is IP block in Vivado. So why we need XADC Wizard? So XADC Wizard, suppose if we do not want to use XADC Wizard, then what we have to do? We have to do a coding, whole code for analog to digital conversion. Okay, say this is the XADC Wizard block. Okay, here there are various things, so I will tell you one by one what these things are. This is, you can see, after selecting the XADC Wizard, I have told you we have to do some modification. So finally, after modifying this XADC Wizard, the final stage, you can see there are various blocks I have used. So don't worry, I will tell you step by step how to do this. Okay, so first open the Vivado software, then go to the create project, and next click on next, give the project name. I am giving the name XADC learn. Okay, and save where you want to save. Next, and do this, please check it, there should be a tick mark on do not specify sources. Click on next and select your FPGA board. So first of all, already I have told you in my previous video, first of all go to the general purpose, category is general purpose, family is RTX 7, and the package is CSG324. okay, speed is -1. After selecting this, we can see there are 5 options. In 5 options, you can see in my case this is the FPGA which I am using. Click on next, finish. So after opening the Vivado software, go to the create block design. Okay, select one name. I am using name XADC block. Okay, click on next. You can see XADC block empty. You can see a design is empty. Press in plus sign to add IP block, or either you can choose click on this one or this one. Okay, so click and search for XADC. You can see after typing XADC, one XADC is came. Click, double click on XADC, where you can see there are different inputs and outputs, which is in our case not required. So what we have to do? We have to do modification. Okay, so double click on XADC Wizard. And after double clicking, you will reach inside the XADC Wizard, and we will do modification here. You can see the component name is XADC Wiz 0. Okay, so what we do in basics, what we select, we do not use XC for light, we are using DRP. So select DRP. Timing mode, select continuous, we do not want event mode. And in startup channel selection, one thing you should know, in FPGA there are in the ADC pins depends on the types of FPGA which you are using. In Nexus 4 board there are 4 ADC pins. So according to your desired, you can select out of 4. Okay, so but in my case I am using single channel. Okay, single channel I am using. If you use multiple channels, then you can select channel sequencer. Okay, and the rest thing, keep it as it is, do not change anything, only the DRP and single channel. Okay, don't click OK. So click on ADC setup and do not change anything. Then go to alarm. As you can see, there are multiple ports, but we do not need alarm signals. You can see there are alarms, various types of alarms. So I am deselecting it. You can see there are ports, the alarm ports are removed. Okay, now go to the single channel. Now I am using single channel, so there are various types of channels for calibration. And for in Nexus 4 FPGA, the channel name is VAUX 2, VAUX 3, VAUX 10 and VAUX 11. So any 4 you can choose. I am using VAUX 11. Okay, VAUX P for positive and VAUX N for negative or ground. Okay, now you can see summary and then click on OK. Okay, and the rest part you can see this is the XADC Wizard. Okay, so you can see here DDI data address, data enable, data in, D out. Okay, but you can't see these things, so this we have to expand it. Okay, after expanding it, you can see data address. So what is data address? Suppose I'm using the VAUX channel VAUX 11, so every channel has a separate data address. Okay, now for VAUX 11 data address is in hexadecimal. If we use hexa, then the data channel of DDR is 1B. Okay, in hexadecimal. Okay, and this DDR is how many bits? Only 7 bits. 0 to 6 means 7 bit. So if you convert 1B into decimal, so why I am converting it to decimal? Because in this block we have to give address in decimal form. Okay, so the 1B, the decimal of 1B is how much? If you do B is what? 1011. Okay, and the 1 is 01. And the data address is 7 bit. Already we have taken 4 bits. Now only how much bits is required? 1 bit. 3 bit. So 0 0 1. Okay, this value is 1 and this value is B. If we convert this bit binary into decimal, then what we get? We get a decimal value of 27. So this decimal value we have to put in data address. Okay, now after data address there is a DEN in. Okay, so data enable. So data enable, which is, if you see, this data enable is connected to EOC out. Okay, it means what? It means this EOC out gives a signal to data enable. Okay, after receiving data enable signal, then the conversion start. Okay, so that's why EOC is connected to DEN. Now the next is DI in. DI in means, it means if you want to give some inputs, data inputs, so you can give, but in this case data input is, I have chosen 0 value. Inside this I have decimal value chosen is 0. We will see. Okay, and data write. Okay, so data DWE means data write. Okay, so we do not want to write any data, so this value is also 0. This is 27, this is 27, this value is 0 0. Okay, and okay, now after this is VP, and this is already this is also a ADC pin, but this one is inside the FPGA, which we can't use it. Okay, so make it 0 input. So as you can see, this 0 decimal value is given, I am giving to DWE and BN and VP both. Okay, now this is our ADC pin, VAUX N11 and VAUX P11. You can see the input is coming. Input is coming to the VAUX pin, means digital, analog input is coming. This analog is converted to digital. Okay, this analog is converted to digital. Okay, and now in the last there is a clock. So and in output side you can see alarm out, EOS out, which is not required, so we do not use it, keep it as it is. This channel out is required for multiple channels. If I use multiple channels, this is a channel selection, so according to your channel it will select. Okay, but in my case I am using only one channel, that is why we not required channel out. Okay, now you may ask where we get output. Okay, so output port you can see DO out. Okay, this is a 16 bit, 0 to 15, 16 bit. Now this DO port is connected to one slice block. Okay, why? Because we want only 12 bit data. So slice the LSB 4 bit and provide the rest 12 bit data, and from this we get our digital output. Okay, from this we get the final digital output. I hope you understand. Now let's go to the Vivado software and do one by one. So first of all, what we do, as I told you, first we have to connect this EOC with the data enable. Okay, data enable port. So let's zoom this. Yes. Now data address. So what we need, a constant block. So add a constant. See, constant, search for constant. Okay, double click. This is the constant block. Connect with the data address. Okay, so this constant block, so data output, how much width is how much, 7 bit, and the value is 27 decimal value. Okay, click OK. Now the next is DI in, which is 0, so we need another constant block, so copy it and paste. Okay, now connect with data in, and this is 16 bit, so we need a 16 bit, width is 16 bit we need, and the decimal value is 0. Okay, now DO out we will do later. And now the next part is data ready. This is data ready. So data ready you may connect with LED, so it will, if the data is ready, then it will show you the through LED will blink or any kind of anything you this is the output port, you can take anything in output. So data ready, in this case data ready is not taken, I think. Okay, so data ready is not taken, so keep it, so do not take the. So DWE, data write, so data write also I have to make it 0, so copy and paste one more block, constant block, and connect with DWE. Also we connect with which, connect with VPN, sorry VPN not VN and VN I am not using. So click, double click, width is 1 bit only and the value is 0 already. Okay, click OK. And next VAUX. So this is our input port, so make it input. So click on this and right click and select for make external. Okay, similarly for VAUX P, make it external. Okay, now this clock part, so for clock is also input, so as you can see the clock is also input, so make it external. Okay, so these are the actual input port. Okay, so reset pin is not required, so if you do not want, then double click it and you can see in basic there is a reset in, so click on reset in and OK, then the reset pin is removed. Now the next part is data out. Okay, so data out, for this I have told you this is 16 bit, but we want only 12 bit. 12 bit is enough. Okay, so now click on add and search for slice, double click, and this is the optimized routing. If you click it, then the routing which is the random routing will optimize. Okay, now this is the slice, so you can see data in is 31, but we need data bit, but we in our case data in is 16 bit, so double click and with select 16 and select DI width, the input width is 16 and the input from, this is the MSB, so from 15 how much we want, from 15 to 4 it is 12 bit, so 3210 is removed. Okay, and the DO out width is 12, so click on OK. You can see if we zoom in, then you can see DI in is 15, 0 means 16 bit, and after slicing DI out is 12 bit. Okay, So connect it with the DO out, connect it and make it external. This is our actual output, so make it external. Okay, now our configuration is completed and optimize this. This is our final configuration of XADC Wizard. So what we will do next? So this is only to XADC block. Okay, XADC block, suppose this is as I have told you in this case, in converter, and you can see yeah, this output is, suppose this output is VAUX N and VAUX P coming ADC block. So this whole ADC is this one. Okay, this one is the whole ADC block where the clock is input and the analog VAUX N and P are input. Okay, and the output, this is the output. The output is fed to the our controller FPGA. Okay, so this is the and the rest part we will do, the configuration is completed. Now the next is we will do simulation part. So the simulation part we will do in next video. Okay, so thank you for watching this video.